Hi there! Welcome to the fourth episode of the filters tutorial. Today we will talk about the passive RL low-pass filters, and we will examine both the first order and the second order filters. As well as the previous episodes, the most part of this video is dedicated to lab experiments to show you how these filters work by taking some measurements on them. And this time I will also show you a different method for measuring the cutoff frequency, which could be easier and more meaningful to some of you. Before moving on, please take a moment to also subscribe to the channel and don't forget to click on the notification bell. That will set up an automatic notification every time a new video comes out. Make sure also to set up your YouTube account to receive such notifications both on the computer browser and on your smartphone. I have also added in the video description below an affiliate link that you can use to buy stuff on Amazon and at the same time support my channel at no cost to you. In the same description there are also links to Patreon and PayPal, so you can support the channel with money donations if you are so inclined. And now, let's begin. The schematic of a first-order RL low-pass filter has the same shape of the RC one. But now the capacitor is replaced with a resistor, and the resistor is replaced by an inductor. If we consider the voltage divider made of L and R, we can say that the output voltage is a fraction of the input voltage that depends on the angular frequency of the input signal. The transfer function of this circuit, given by the ratio of the output voltage and the input voltage, is therefore the following, which we can write this other way by dividing both numerator and denominator by R. We can now define the natural angular frequency of this circuit as R over L, and we can call it omega 0, so omega 0 equals R over L. Substituting R over L in the transfer function with omega 0, we get the known transfer function of the first-order low-pass filters. From here, we can calculate the cutoff frequency of such a filter, recalling that the cutoff frequency is the value at which the magnitude of the transfer function equals 1 over square root of 2. And since the numerators of this equation are both 1, it means that the denominators must also be equal to each other. And so, we can write that the magnitude of 1 plus j omega c over omega 0 equals square root of 2. Resolving this equation, we finally find that omega c, the angular cutoff frequency, equals the natural frequency of the circuit, and so omega c equals R over L. And finally, recalling that the frequency is obtained dividing the angular frequency by 2 pi, we get the formula to determine the cutoff frequency of the first-order RL low-pass filter, which is 1 over 2 pi times R over L. Let's now take a look from a qualitatively point of view on how the response to the various frequencies of such filter looks like. Here is a drawing of the magnitude as a function of the frequency for the RL first-order low-pass filter. You will notice immediately that this curve looks exactly like the one for the corresponding RC filter. And, in fact, if you think about it, at the lowest frequencies the inductor behaves just like a resistor of very low value, practically 0 ohms, and so the voltage divider composed by it and the resistor R brings the total amount of voltage present at the input exactly equals to the output. But if we start increasing the frequency, the inductor will start presenting its inductive reactance, which will increase at the increase of the frequency. Such reactance will behave like a resistor, and the higher is the reactance, the higher will be the equivalent resistance. And so, the voltage divider at some point will allow less and less voltage to go from the input to the output. Then, because the reactance is at the denominator of the transfer function, the magnitude of the transfer function will start actually decreasing exponentially. The representation of an exponential curve on a logarithmic diagram is a straight line, and that is in fact what we see happening as the frequency increases more and more. Let's now go to the lab and make some experiment to see if what we have found so far with the theory is reflected in practice. Let's start by examining the circuit that we want to test. As you can see here, we have just an inductor and a resistor. This resistor in particular is of 1 kilo ohm, and this inductor is 10 millihenries. I have connected the inductor in series between this point and this point. These 2 points are both on ground. This resistor is connected on this side, this blue connector and ground, and the green connector connects the inductor with the other end of the circuit. So basically this is the classical RL circuit in the low pass configuration. Since we know the values of this resistor and inductor, let's calculate what is the expected cutoff frequency that we are looking for. So very quickly, our circuit is made like this. There is an inductor, L, there is a resistor over here, then there are these 2 test points on the base, and these other 2 test points on the upper side. So you can see the perfect alignment of the components in exactly the same way. Now, how we have already learned, the cutoff frequency of this device is given by 1 over 2 pi R over L. Now in our case we have 1 over 2 pi, R is 1 kilo ohm and L is 10 millihenry. The result of this calculation gives us a value of exactly 15.92 kHz. Let's see if this is the same value that we would find measuring the cutoff frequency directly on the circuit. To take the measurements, I'm gonna do this. I will connect my function generator on this side of the circuit, ground, and the signal over here, and then the other side will be connected to an oscilloscope, ground, and over here. Let's take a look. So this probe goes directly to the oscilloscope up there. Let me enlarge the image so you can see it better. And then we have a function generator over here that is already generating a sine wave of 10,000 kHz at 5 volts peak to peak. Now let's start with a value of frequency very low, so let's start changing that, and let's drop down to about 100 Hz. This time we will evaluate the cutoff frequency. Rather than using the oscilloscope in the frequency domain, we will do it in the time domain, and we will basically measure the moment where the 5 volts are reduced of about 1 over square root of 2, which is basically the minus 3 dB that we are looking for, which are defined as the drop in amplitude of the signal, in magnitude of the signal, at the cutoff frequency. So now let's see on the oscilloscope what's going on. So far I don't see anything, but of course I need to adjust the setup of the oscilloscope. Let's do that. And here's our sine wave. So we are looking for the cutoff frequency, which is basically when this signal will go down of 1 over square root of 2, which is around 0.7. So let me use the cursors directly over here. I will set the cursor to read voltage, and the start cursor will go, let me set them up first, so we need to go with the start cursor first. So I'm gonna set it just on top of the sine wave, right there, and then I will move to the other cursor and I will set it such that I will have a delta V of about 700 millivolt. Apparently I cannot have those because the oscilloscope gives me either 720 or 680 millivolts. So let me take this one, and let's consider that the frequency has to be a little, just a touch higher than what we are gonna measure. So let's go now. Let's increase the value of this frequency. Let's go to 1 kHz first. And as you can see right now, the edge of the sine wave is still at the maximum, so there is no attenuation of the signal so far. Now I'm gonna go to 5000 Hz, 5 kHz, as you can see from here, and again there is almost no change over here. Maybe there is just a touch of attenuation, but still we are far away from the cutoff frequency. So let me increase it further, and as you can see now we are seeing the signal becoming smaller. So let's go on a little bit further. Okay, I guess we are gonna stop over here, just above the line, because the line will be actually 0.72 instead of 0.7. So this should be enough. And we are seeing a frequency of 16 kHz at this point. So this is about the cutoff frequency that we are looking for. And actually, if you remember the calculation we just made, the theoretical value for this cutoff frequency should be 15.92 kHz. Here. So, it's very close, and as you can see, it's really easy to do the measurements in this way once you have available the cursors. But let's check another thing now. So let me connect the other channel of the oscilloscope to the output of the function generator. This way I will be able to see at the same time both waves, the original one and the one attenuated. And let's see what's the difference between the two. Let me start back again from 100 Hz. So let me go down. Here we go. Let's center everything here. Here's the waves at 100 Hz. Right now these two waves are basically identical because there is no attenuation on 100 Hz. Let's overimpose one on the other so we can see what happened when the frequency changed. Much easier. So let me center this one and then this one. As you can see, they are basically almost overimposed. Now let me increase the frequency. Let's move to 1000 Hz again. You can see there is basically no change, almost no change. You can see there is a little bit of yellow coming out of here. Yellow is basically the signal after the filter, at the output of the filter. Blue is the signal generated by the function generator, so it's the source. So let's go now to increase further the frequencies. This is 5 kHz. Look at that. You can see there is a phase shift between the input voltage in blue and the output voltage in yellow. And you can see that this time the output voltage is delaying with respect to the input voltage. You can see basically that the yellow comes right after the blue, which means that once the signal reaches a certain level on the input, the same level is reached on the output only after a while. So we say that the signal on the output is getting behind. And if we do this any further, if we keep increasing the frequency, look what's happening. Now I'm going to the cutoff frequency, right here. Look at that. Basically, let me center this so you can see this better. At the cutoff frequency, we are at about 45 degrees displacement. So basically it's 1/4 of the wavelength. You see that? We have the top and we have just 1/4 of the wavelength over there. So basically this tells us that at the cutoff frequency the phase shift is minus 45 degrees. Let's keep going up now with the frequency and let's see what happened for greater values of the frequency. Okay, let me increase this a little bit so we can better see what's going on, otherwise we won't be able to see exactly what happened. Okay, here we are. Look at this now. Let me center again on the blue wave. Look, when the blue wave is at its top, so is already at 90 degrees from the beginning of the sine wave of the output is just about to begin. So we have a 90 degree phase shift, negative 90 degrees, because the output of the filter is basically lagging behind the input. To obtain the schematic of a second-order RL low-pass filter, we just cascade two first-order RL low-pass filters. If we consider the two inductors with the same value of inductance, and likewise for the two resistors, resolving this circuit we find that the transfer function is given by 1 over the sum of 1, 3j omega over omega 0 and negative omega square over omega 0 square, once we define omega 0 as R over L. To find the cutoff angular frequency, we substitute omega with omega c, and we impose that the magnitude of this expression equals 1 over square root of 2. Again, since the numerators are the same, also the denominators must be equal to each other, and therefore we can write the expression that allows us to find the angular cutoff frequency, which after all the calculations are done equals to 0.374 times the natural frequency, as we expected, since what we said about the second-order RC low-pass filters. And so, for the second-order RL low-pass filters, the cutoff frequency is 0.374 times the cutoff frequency of the first-order RL low-pass filter. If you remember the previous video on the second-order RC low-pass filter, I'm sure you are already thinking that if we put two first-order RL filters in series, we will obtain a new magnitude curve that has a slope double the amount of the first-order filter. And in fact, this is exactly what happens. Moreover, as we have already seen with the calculations, the cutoff frequency will be lower than the first-order filter. The explanation for that is basically the same. Because the two magnitude diagrams will add up, at the point of the cutoff frequency of the first-order filter, the attenuation is 3 dB, but for the second-order filter, at the same frequency, the attenuation will be minus 6 dB. To find the minus 3 dB again, we have to move toward the left of the graphic, and therefore the new cutoff frequency will be lower for the second filter than it is for the first-order filter. Let's go again in the lab now, and let's check if the theory is still sound. To see what happened with the second-order low-pass filter, I built a second circuit exactly identical to the first one. So we have two first-order low-pass filters. And now I will connect the output of the first filter to the input of the next, exactly like we did with the RC filters. So this is the output that goes to the input of the second filter, and this one is ground connection on both of them. So now I'm gonna connect the function generator again to this filter. And then I'm going to connect the yellow channel, channel 1 of the oscilloscope, to the output of the second filter. And here is what we see on the oscilloscope for a frequency of 100 Hz. You can see it's practically basically identical to the case of the first order filter. But let's see now what happened when we start increasing the frequency. Let's go again to 1 kHz. And let me overimpose the two waves again. Look, already we can see a little shift ahead of the yellow signal, moving on the right, so basically it takes more time for the output to come out identical at the input. And then it's already just a little smaller. Let me increase both signals so you can see them better. Right now they are comparable, both 1 volts of sensitivity per division. So now let's go further with the frequency. Oh, actually, let me do this. Let me go back to 100 Hz so we can do two things at the same time. So I'm gonna put again the cursors here. And the voltage. And the start cursor is already at the right place. And the end cursor also, you can see, is 720 millivolts. So basically we have already the cursor set from the previous case. And we just need to wait until the yellow signal goes down to the second cursor, the end cursor, to determine which one is the cutoff frequency. So now that we have this set, let's go ahead and increase the frequency again. So 1 kHz. And you can see how there is already a little shift and a little decrease of the amplitude of the signal. So there is an increase in attenuation. Now let's move to 2 kHz. Look at that. 3 kHz. Look how this time the wave goes down quite faster. And this is 4 kHz. 5 kHz. This is already 6 kHz. And I guess we can stop over here, because if we go any further, we go beyond. So this is the place where we have to wait. Here we go. So basically we have a cutoff frequency of about 6 kHz. And this because we put in series two identical first order low pass filter, which the original cutoff frequency was 16 kHz. So you can see now how things change from the perspective of the second order filters. So let's now keep increasing the frequency and let's see what happened. As you can see, things keep changing very fast. So this is basically the cutoff frequency right now of the single first order low pass filter. With two in series, you can see how the signal is now much lower, and this confirms that now we are going at 40 dB attenuation per decade rather than 20 dB attenuation per decade for the case of the first order filter. And so you can see how the second order filter behaves at the change of the frequency. So now, before concluding, let's take a look at one last case. Basically, in this case I have the two first order low pass filters again connected in series, but I have one channel of the oscilloscope, the blue one, connected to the output of the first order low pass filter, and the other channel of the oscilloscope, the yellow one, connected to the output of the second order low pass filter. Let's see what difference there is with respect to the response of a square wave, like this one here. So as you can see, I have a square wave at low frequency. What we are interested in right now is how long it takes for the output signal to complete the change from the 0 volt to the 5 volts signal. Let's take a look at the oscilloscope and let's see what we see over here. The blue one is the output of the first order low pass filter, and the yellow one is the output of the second order low pass filter. As you can see, the response to the square wave is faster for the first order low pass filter and a little slower for the second order low pass filter. You see how smoother this line is with respect to this one. And this is because there is a greater amount of attenuation here for the various frequency, the harmonics of the square wave, than there is over here, where the attenuation is less. Let's take a look now at the other end, basically when the signal goes down. See again. While for the first order low pass filter the signal goes down very fast, For the second order low-pass filter, the signal goes down slower, again because they are missing more high frequencies, and so everything slows down accordingly. Let me superpose them so you can have a better look at what is going on. See, there is a difference here between the two signals, the yellow one and the blue one. And with that, we can consider this subject completed. So thank you for following me to the end of this video, and I hope you enjoyed watching this video as much as I enjoyed making it, and that you found interesting and fun to view how the theory of the low-pass filters matches exactly the practice. Next time we will start talking about high-pass filters, and we will see how easy it is, with the same components we used for the low-pass filters, to build new filters that have exactly the opposite characteristics of the low-pass filters. Don't forget to subscribe to the channel so you won't miss the next episodes. And now thank you for watching, see you in the next video, and as usual, happy experiments!